Good morning. Next is we discuss the structure of benzene. Benzene. We know that the benzene is, we represent benzene, the structure of benzene is like this, or we can see that the position of the double bond is changing. Here you can see that the double bond is between these two carbon, and in this structure this double bond is the position of the double bond is changed, or it can be represented like this. Okay, now that means actually in benzene the double bond is not a pure double bond and the single bond is not a pure single bond, because in the first structure you can see that this is double bond, and in the second structure it is changed to a single bond. In the first structure this bond, the bond between these two carbon is a single bond, but here it will become a double bond. That means in benzene the double bond is not actually a pure double bond, or the single bond is not a pure single bond. So how we can explain the change in the position of the double bond? We can explain this Kekule's resonance structure of benzene on the basis of molecular orbital concept. How we get the double bond? Here the double bond is between these two carbon, and here these two carbon, and it is between these two carbon. But in this second structure, that the position of the double bond is changed. This we can explain on the basis of molecular orbital structure of benzene. Molecular orbital structure. Okay, and in benzene the carbon atom is in Sp2 hybridized state. Okay, in benzene, that's the first point you have to remember. Carbon atom is in Sp2 hybridized state. Sp2 hybridized state. That means carbon ground state electronic configuration C6, 1s2, 2s2, 2p2, 1s2, 2s2, 2p2, and here 1s2, this is 1s2, and here it is 2s2, and here it is 2p2, means 2px1 and 2py1. Okay, and in the excited state this is ground state, and in the excited state what will happen? As we have discussed, one of the 2s electron will be shifted to the vacant p orbital. Therefore we get again here no change, 1s2. Here it will become only one electron, and here you can see that say 2px1, 2py1, and one of the 2s electron is shifting to here. Here it will also become one electron. Okay, now Sp2 hybridized state means what is that? One s electron and 2p electron. This will mix together and we get three hybridized orbital. That means when we mix 1s and 2p orbital, how many hybridized orbital we will get? We get 3 hybridized orbital. Okay, here you can see that we are getting 3 hybridized orbital. Each hybridized orbital is known as sp2. This is sp2, this is also sp2, this is also sp2. Why it is called sp2? Because it is formed by mixing 1s and 2p, therefore sp2, and here you are getting one unhybridized p orbital, pure p orbital, unhybridized p orbital. That last p orbital is not taking part in the hybridization. Therefore since carbon atom is in sp2 hybridized state, we are getting 3 hybridized orbital and 1 unhybridized pure orbital. Now look at here the structure of benzene. Here you can see that 1, 2, 3, 4, 5, 6. Okay, and I told you each carbon atom is in the sp2 hybridized state. That means there are 3 sp2 hybridized orbital, 3 sp2 hybridized orbital. This is sp2 1, and here also 2, and here also, okay, 3. These 3 are sp2 hybridized orbitals, sp2 hybridized orbitals. And what is there? There is one unhybridized p orbital. I will show the unhybridized orbital later. Okay, now this carbon, again this carbon, we are coming to this carbon. This carbon is also having 3 hybridized orbital. What is that? This is sp2 hybridized orbital. Here also sp2 hybridized orbital, and here also you can see one sp2 hybridized orbital. These are all sp2 hybridized orbitals, second carbon. Now if we come to third carbon, here you can see that sp2, this is sp2 hybridized orbital, and here also sp2 hybridized orbital, and this is the third sp2 hybridized orbital. Okay, now I am coming to this carbon. This is sp2 hybridized orbital, second sp2 hybridized, and third sp2 hybridized orbital. Okay, and here you can see that this is the last carbon. 1, 2, 3, 4. Here is another carbon. Okay, look at it here. See this sp2 hybridized orbital, sp2, and here you can see that this is also sp2. Okay, and the last carbon here is, you can see that this carbon, this is sp2, and here is also sp2. This is third one. Okay, so once again, look at it here, the carbon atom, the actual structure of benzene is, look at it here, benzene. How you can write benzene here? When you draw the structure of benzene, here is carbon, carbon. Okay, here is also carbon, carbon. Okay, carbon, carbon. That means there are 6 carbon, and here is hydrogen. Okay, hydrogen is here, hydrogen. Okay. Okay, then what will come? Alternate double and single bond. Alternate double and single bond. Okay, how this structure is coming? Look at here, how this structure is coming. This structure means, here you can see that, look at the position of the double bond. The double bond is here, second double bond, and the third double bond. Okay, look at here. And since carbon atom is in sp2 hybridized state, how many sp2 hybridized orbitals are there? There are 3 sp2 hybridized orbitals for each carbon atom. First carbon 1, 2, 3. Second carbon 1, 2, 3. Third carbon 1, 2, 3. Fourth carbon 1, 2, 3. Fifth one, look at here, 1, 2, 3. And the sixth one also, there are 3 sp2 hybridized orbital. Now you can see that in each carbon there is an unhybridized p orbital. Unhybridized p orbital. You look at here, unhybridized p orbital. Okay, here is unhybridized p orbital, or I can show like this. This is unhybridized p orbital, unhybridized p orbital in the first carbon, and here also you can see that unhybridized p orbital in the second carbon, unhybridized p orbital in the second carbon, and in the third carbon again this is unhybridized p orbital. Okay. Okay, unhybridized p orbital, and in here also you can see that unhybridized p orbital. Okay, and in this structure you can see that here is this is unhybridized p orbital, and here also unhybridized p orbital. Okay, these are unhybridized p orbital present in each carbon atom. Now look at here. First carbon, this is sp2, and the second carbon, this is also sp2. This will overlap. Okay, that means you are getting the first, here is a sigma bond, here is a sigma bond. This sigma bond is forming. Okay, CC sigma bond is formed by the end-to-end end overlapping of a sp2 hybridized orbital. Now look at here. In this carbon, this is sp2, this is sp2, and for this carbon, this is also sp2. Here also you can see that end-to-end overlapping of a hybridized sp2 orbitals. Therefore, you are getting this CC sigma bond, and you can see that this carbon, this is sp2, and for this carbon, this is also sp2. They will overlap end-to-end, and you are getting this CC sigma bond. This is sigma bond, and here also you can see that the sp2 orbital of this carbon and this carbon, they will overlap, and you are getting this CC sigma bond. And here also you can see that the carbon sp2 hybridized orbital is end-to-end overlapping is taking place, and you are getting this bond. And finally you can see that this carbon and this carbon, their sp2 hybridized orbital will overlap and you are getting this CC sigma bond. This is the way of how CC sigma bond is forming. Okay, by the sp2 hybridized orbital overlapping of carbon atom, between carbon atom, we are getting all the CC sigma bonds. Okay, now look at here. Here is our hydrogen. First hydrogen, s orbital of hydrogen is overlapping with the sp2 orbital of carbon. Okay, so what will form? sp2 s orbital, then you are getting CH sigma bond here. This will result in the formation of a sigma bond between carbon and hydrogen. This bond is forming, and the second hydrogen, its s orbital will overlap with sp2 hybridized orbital of carbon. You are getting CH sigma bond. This CH sigma bond is forming. Next hydrogen, okay, here also you are getting this CH sigma bond is forming, and here you can see that hydrogen is overlapping. It is CH sigma bond, and here also hydrogen CH sigma bond, and here is also hydrogen. You are getting CH sigma bond. How many CH bonds are forming? 1, 2, 3, 4, 5, 6. 6 CH sigma bonds are formed. Now, how the double bond is forming? Look at here, how the double bond is forming between carbon and carbon. Now you can see that in the first carbon there is unhybridized p orbital, and in the second carbon also there is unhybridized p orbital. And what will happen? This unhybridized p orbital will overlap sideways. So this upper half will overlap and the lower half will overlap, which will result in the formation of a pi bond. Okay, here is a pi bond between these two carbon. The unhybridized p orbital will overlap sideways, and which will result in the formation of a pi bond. And look at here, here also you can see that this lobe will overlap, and this upper lobe will overlap, which will result in the formation of the second pi bond. And look at here, you can see that this unhybridized p orbital will overlap, upper lobe will overlap, and here is a lower lobe will overlap, which will result in the formation of the third pi bond. Clear? So because of this orbital overlapping, okay, which this structure you are getting. This structure means here look at the position of the double bond. Double bond is between these two carbon and these two carbon and these two carbon. Okay. Now how we are getting the next structure? That means the double bond is here. The double bond is between these two carbon. We know that in benzene, the next moment you can see that the double bond is can be here. So how the double bond is changed to between these two carbon, or how the double bond is coming between these two and these two and these two. Look at it here. The explanation for that one. So now in the second case, look at it here. The orbital overlapping is in a different way. So here you can see that in the second case, look at it here. In the first case we discussed the unhybridized p orbital. These two p orbital will overlap. These that means this orbital and this p orbital will overlap sideways, and which is resulting in the formation of the CC double bond. In the next case, you can see that the unhybridized p orbital of this carbon will overlap. See, between these two carbon, the upper lobe will overlap and the lower lobe will overlap. Therefore, which will result in the formation of a pi bond between these two carbon. Here is the pi bond. Okay, because the unhybridized p orbital is overlapping between these two carbon atom of the p orbital of between these two carbon atom. And in the next case, what will happen? This will overlap. Okay, here and you can see that unhybridized orbital of this carbon and this carbon. So unhybridized p orbital of these two carbon will overlap, and which will result in the formation of a pi bond between these two carbon. Here is the pi bond. Okay, and in the next case, what is happening? The p orbital of between these two carbon, the p orbital of these two carbon will overlap sideways, and which will result in the formation of a pi bond between these two carbon. Means the pi bond is coming here. Okay, so this type of orbital overlapping is possible in benzene. Therefore, what will happen? We are getting a resonance structure. For resonance structure, that means the position of the double bond is keep on changing and keep on changing, and this is the explanation for why the double bond is becoming a single bond and the single bond is becoming a double bond in benzene. Okay, hope it is clear for you. Thank you.